Hey everyone, this is Big Brother Engineer. Welcome to today's video. Just a few notes before I start this video. I go through a lot of files, a presentation, an Excel sheet, lots of files in this video. So what I'm going to do is I'm going to leave a link in the description for all the files I have in this video. And this is going to be a Google Drive link. So if you just go onto the Google Drive link that I'll leave in the description, download the folder and extract the files to your computer, then you can use all the files. And the files that I have in this file is firstly this NACA2412 file, and this is the file which I start the tutorial with and go through a walkthrough through the whole video with this file. Secondly, then this is the file that I make some edits to during the video. And then lastly, the file NACA2412 Mesh Independence is the final file with everything completed in for you to compare your final results to. And also the Excel sheet I use is here, and the slides I go through is here. The structure of this video is a little bit different to my previous videos where I'm either doing a lecture or tutorial. In today's video, what I'm going to do is go through the theory behind a Mesh Independence Study for the first few minutes, and then I'm going to jump into a practical example in Ansys Fluent. But if you're just interested in just a lecture or just a tutorial, I will leave timestamps in the description as well for you to jump to what you think is most important for you. But again, I would encourage you to watch the whole video, both the theory and the practical side. Because I think you will learn a lot by going through the notes and then following the tutorial and following with the steps that I provide in this video. But without further ado, I hope you enjoy the video. Hey everyone, this is Big Brother Engineering and welcome to this talk on mesh refinement in CFD. Today we're going to talk about CFD verification and validation, as it's very important to understand this when conducting a mesh independence study. I'm also going to go through the grid convergence index method, which is how we conduct mesh independent studies for publication level journals. And then lastly, I'll go through a very practical example in Ansys Student of an airfoil, and we'll take the NACA2412 example that I did in the previous video, conduct a mesh independent study on that and compare it with experimental data. So in CFD, we have verification and validation, and these are two different things. So verification is a check that we do on our simulation to ensure that we have solved the set of equations right. So what we're doing is we're essentially checking that the mathematical solution that we were attempting to solve by using our CFD solver has solved the equations right. So have we solved our mathematical equations correctly? And then we have validation, and this is a little bit different. Validation is when we compare the CFD results that we get on the computer and compare with reality. And this is checking if we've solved the right equations. So you can see how there's a difference here, because we could verify that our computer code has solved our solution right, but if we're not modeling the correct thing from reality, then we're of course going to get the wrong solution if we're running something with the wrong velocity or wrong geometry. And of course we wouldn't be able to represent the experiment correctly. So this is very important to understand, because when we're conducting a mesh independent study, we're only verifying the solution. We can't actually validate that our modeling assumptions that we're using are actually correct. In CFD verification, there are three main errors: the iterative error, the round off error, and the discretization error. So the discretization error would be the error associated with taking our partial differential equations and reducing it into discretized equations. In other words, the effect that the mesh has on our actual solution. So these are the three main errors that are associated with CFD verification. So the iterative error, and this is the error that's associated with the fact that we have to solve nonlinear equations with our CFD solver. So obviously the Navier-Stokes equations, as I talked about in my last video, are nonlinear, and we have to use an iterative approach to solve these equations. And if we were to iterate our solution for a very, very long time, we would get a so-called solution that has converged to machine accuracy. And this is the most accurate solution that our computer can get in terms of lowering the iterative error. But in reality, when we're running a CFD simulation, we just let the residuals fall below a certain value, say 10e to the minus 3 or 10e to the minus 6, and we stop the iterations. We say this is converged good enough for us, and we're happy to take our results. Now, the difference between when we stop our results and the solution that has converged to machine accuracy, that is the iterative error. And when we're conducting a mesh independence study or a mesh refinement study, we need to ensure that our iterative error is small enough. And I've left a reference there to say that the residuals, the normalized residuals, should decrease by 3 orders of magnitude, which would be in Ansys drop below 10 e to the minus 3. But I would recommend letting the residuals drop below a lower value, say 10 e to the minus 6, if you have a very steady, easy to convert solution, because it really shouldn't take that much longer to fall below 10 e to the minus 6. So our goal is to reduce that iterative error as low as we can when doing a mesh independent study, but we also want to reduce our round off error. And we can reduce this round off error by simply using a double precision solver. This round off error is introduced by the fact that we have only a certain amount of available digits on a computer to solve our equations. So there'll be a certain round off error associated with that. And yeah, in reality, there's not too much more we can do to reduce this round off error other than using a double precision solver. So by ticking this button as we're starting up Fluent. And then finally, we have our discretization error. And the discretization error is going to be the difference between the mathematical solution and the solution that has converged to machine accuracy. So in Ansys, when we're taking our domain and we're dividing it into little chunks, that what we're essentially doing is taking partial differential equations and reducing them into algebraic equations that we're only going to solve at the cell centers, and that gives us an associated discretization error. And this is what we're going to be exploring today. And it's very important that in order to study this, we need to have a small iterative error and a small round off error. And I've in the references that I've cited, it states the importance of this, so I'd recommend reading that if you are interested in doing so. But what we'll do in this study is essentially assume that we have negligible iterative and round off errors, and we'll do so by letting the residuals converge to a sufficient level of accuracy, and by using a double precision solver. And then that will let us estimate our discretization error, which is the error that's associated with meshing the domain. So how do we conduct a mesh independence study in CFD? Well, a very simple way to do this would be simply to take a variable that you're interested in, which I've just called phi in this example, and this could be lift coefficient, drag coefficient, pressure at a certain location, temperature, etc. Whatever variable that you're solving for using your CFD, and plot it at a certain mesh, and then run your simulation with maybe 3 to 5 different meshes and plot how your variable phi changes with the mesh. And you can simply say, in most cases, the variable phi will converge to a certain value, and you'll say that your mesh is your solution has sufficiently converged, and your solution is mesh independent, because as you refine the mesh, the variable phi starts changing less and less. And that's the most simple way to do a mesh independent study. And if you're someone that's conducting a project right now, maybe a bachelor's or a master's, and you just want to get something done quick, this is a very simple way to do it, and it's not very difficult to do. Run your simulation with 3 to 5 different meshes, and plot the variable that you're interested in, the variable phi against the number of cells, and simply plot it on a curve like this, and the variable should not be changing too much as the mesh gets very fine. An alternative approach is to go through the procedure outlined by the Journal of Fluids Engineering, which is the grid convergence index method, and this is the kind of mesh independent studies that are conducted at publication level standards, and I've left a reference there to the procedure. But this is quite a good method. It's not too difficult to conduct, and it will give us a percentage error from our mesh independent study, which is quite good. So this is the method that I'm going to go through today. Before we go through the grid convergence index method, it is important to note that the variable phi can behave in 4 different ways as the mesh is refined. It can behave in a monotonic convergence manner, a monotonic divergence manner, oscillatory convergence, or oscillatory divergence. And the grid convergence index method only works if the variable phi behaves in a monotonic convergence and oscillatory convergence manner. But in today's talk, I'm only going to consider the case where phi converges monotonically, so just the first case here. And the reason for that is there is some uncertainty associated when the variable phi behaves in the oscillatory convergence manner. And in the method by Roach in 1997, it's assumed that the variable phi behaves in a monotonic convergence manner. So I'm just going to go through the case where phi converges monotonically today. So what is monotonic convergence and monotonic divergence? Monotonic convergence is when, as we refine the mesh, so n here represents the number of cells and phi is the variable that we're interested in. As we increase the number of cells, monotonic convergence assumes that the variable phi goes in the same direction, so it always increases or decreases, for example, and the delta phi gets smaller as n increases. And you can clearly see here on the graph that as you increase the number of cell size, the amount that phi changes gets smaller and smaller and smaller. And not only that, the curve is going in the same direction. So monotonic lets us know that the curve is going in the same direction, and the convergence lets us know that the delta phi is getting smaller each time. So for the grid convergence index method that we're using today, we're hoping for this monotonic convergence method, and if phi behaves in any other way, we're just simply going to neglect it. And I've left some numbers here to also show you what monotonic convergence looks like, with some actual numbers instead of just the figure here. The variable phi can also behave in a monotonic divergence way, where as we increase the mesh, the variable phi is going in the same direction each time, but the delta phi now keeps increasing as we increase the number of cell sizes. So you can see that as the mesh gets finer and finer, this variable phi is not approaching one particular value. So we cannot use the grid convergence index method when monotonic divergence appears for the variable phi. And then finally we have oscillatory convergence and oscillatory divergence. First, let's look at oscillatory convergence, and this is what occurs when the variable phi keeps changing direction each time as we increase the number of cells. So it might decrease, then increase, then decrease and increase, etc. This is where the word oscillatory comes from. But the convergence comes from the fact that the change in phi actually decreases as we increase the number of cell sizes. So the delta phi is actually getting smaller each time, but it's oscillating since the phi is decreasing and then increasing and decreasing. So this is what oscillatory convergence is. And then finally, oscillatory divergence, possibly the worst behavior of phi we could get, is when the variable phi keeps changing direction each time in terms of it changing from a low to a high value, and the delta phi actually increases as the mesh increases, as the number of cells increase. So looking at these behaviors here, we're hoping to get this monotonic convergence behavior, as this is the only method that we're assuming the grid convergence index method works for in today's talk. Okay, there is one more thing I need to mention here before I move on to the grid convergence index method, and that's how we reduce the number of cells in a structured manner. And let's take the example where we have a mesh with a 2mm cell size, and this is a 2D mesh, and we want to halve the number of cells in our mesh. What you'll notice is that if we were to just halve the cell size and hope that would halve the number of cells in our mesh, and what we would actually get is 4 times the number of cells in our mesh as we had before. And that's because obviously we have a 2-dimensional mesh. So if we halve the cell size in one direction here and we halve the cell size in the other direction, we're going to end up quadrupling the number of cells. So we need to come up with a different method in order to reduce the cell size in order to get a structured number of cells in each mesh. So to halve the number of cell size or to triple the number of cells, we need to come up with a certain refinement factor in order to do that. And so for this example where we have a 2mm mesh and we want to halve the number of cells, what we would actually need to do is to reduce this 2mm by a factor of √2. And that's simply because if we reduce it by a factor of √2 here and a factor of √2 here, √2 squared would give us 2, and that would halve the number of cell sizes. And I've just left a note here about in 3D that if we were to halve the cell size in a 3D mesh, you would actually 8 times the number of cells. So you can see how using a refinement factor here of 2 would be maybe not so good an idea, because the difference between your medium mesh and your fine mesh would be 8 times, which would it would take far too long to run your fine solution. So for a 3D case, when you're looking to reduce the number of cells by a factor of 2, you should reduce the cell size by a factor of a cubed root of 2, because if you reduce it by a cubed root of 2 here, and in the third direction, that would reduce the number of cells by a factor of 2. And that leads us to the first step in the grid convergence index method, and that's to define your characteristic cell size. And for 2D, what that would be is if you were to sum up the sum of the areas of your cells and divide that by the number of cells and multiply that by the power of a half, and that would give you your characteristic cell size. And for this case here, if you have a structured mesh, our characteristic cell size would simply be this 2 millimeters here. But this case here is for an unstructured mesh. We can simply sum the areas up and divide it by the number of cells, multiplied by the power of a half, and that would give you a characteristic cell size that represents the whole mesh. And similarly for a 3D unstructured mesh, you can use the volumes to get a characteristic cell size that represents the size of the whole mesh. The next step then, after we have our characteristic cell size, which would be H2 in this case, is to create two other meshes, a fine mesh and a medium mesh with a refinement factor greater than 1.3. So what we're going to do is we're going to create a fine mesh where the cell size of the fine mesh is at least 1.3 times smaller than the medium mesh, and a coarse mesh where the characteristic cell size is at least 1.3 times larger than the medium mesh. And I'll show you where this refinement factor of 1.3 comes from shortly. So let's consider the 2D case that we talked about before and calculate the refinement factor if we reduce the cell size by √2, and let's check if it's greater than this 1.3 factor. So if we were to take our 2 millimeter mesh here, this is the medium mesh, and then we create a fine mesh which is √2 times smaller than the medium mesh. So essentially the fine mesh is going to have a size of 2 millimeters divided by √2. That gives us a refinement factor of √2. So we're reducing the mesh size in the fine mesh to be √2 times smaller than the medium mesh. And √2 is equal to 1.4, so that's greater than 1.3, so that meets this requirement here. And for the 3D case, if we had a 2 millimeter mesh and then we reduce our fine mesh to be the cube root of 2 smaller than the original medium mesh, that would give us a refinement factor of the cube root of 2, which is equal to 1.26, and that's where this 1.3 comes from. You can see that the cube root of 2 is actually equal to 1.26, which is just about equal to 1.3. So essentially what we're doing here is we're going to create 3 meshes with a refinement factor that needs to be greater than 1.3. And 1.3 is the minimum, because what this tells us is that for a 3D mesh, we need to at least double the number of cells for a sufficient refinement factor. Now, you can use a refinement factor of say 1.5 or 2 or 4, but the reason why you might not want to do that is because the fine mesh then might just take way too long to run. So in the case where we had a refinement factor of 2, so in other words the fine mesh had a cell size which was half the original medium mesh, this would be a refinement factor of 2. You could use a refinement factor of 2 if you wanted, but you just note that you will get a mesh size in the fine mesh which is quadruple the size of the original medium mesh. So it's going to take far longer to run that case study than if you were to use a refinement factor of 1.3 or 1.412. So now we've created 3 meshes with a constant refinement factor, and that refinement factor needs to be greater than 1.3. And to keep it simple for the 2D case, I'm just going to use a refinement factor of √2, because that essentially doubles the number of cell sizes. Sorry, that essentially doubles the number of cells. The next step then in the grid convergence index method is to run our simulation with our coarse mesh, medium mesh and fine mesh, and to calculate the apparent order of accuracy. And we can do that by using this equation here shown on screen. And epsilon32 here is the difference between the coarse mesh and the medium mesh, and the epsilon21 value is the difference between the medium mesh and the fine mesh. And just take a note of, if we take this value of epsilon21 and divide it by epsilon32 and take a look at this value, that will actually tell us about the behavior of phi as we refine the mesh. So if we get a value of epsilon21 divided by epsilon32 in between 0 and 1, that indicates monotonic convergence, because obviously then this epsilon21 value is smaller than epsilon32, and the positive then indicates that the values are going in the same direction. So we're aiming to get epsilon 21 divided by epsilon 32 in between 0 and 1, as this indicates monotonic convergence. Next is to calculate our extrapolated variable phi, and once we know our refinement factor, or we've calculated our apparent order of accuracy p, we can calculate what phi21 extrapolated is. And what this variable is essentially what our variable phi will approach as the cell size approaches 0. So if we have a lift coefficient and we plot it for 3 different meshes, we calculate p and we know, or we can calculate this this phi extrapolated, which for the case of a lift coefficient would be the extrapolated lift coefficient. This tells us where our lift coefficient is approaching as the cell size approaches 0. The next step then is to calculate our error estimates. So we can calculate the approximate relative error and the extrapolated relative error, and finally we can calculate the grid convergence index, and this is essentially the percentage numerical error in our extrapolated variable. So this is very important because not only have we predicted where the variable phi will go as we refine our mesh down to a cell size of 0 or infinite number of elements, but we've also estimated a percentage numerical error. So this is the value in using a grid convergence index method, because now we can plot our variable phi, we can estimate where our variable is approaching, and we can give a percentage numerical error. And this is why this procedure is followed in publication level standard papers, because you can get a percentage error, and you're following a very structured procedure for your mesh refinement studies. And this is why I like this method. Now let's put this to practice for the NACA2412 example that I conducted in a few videos back. I'm going to take the NACA2412, the 2D case from a few videos back that I uploaded, and I'm going to run that study with 3 grids with a refinement factor of √2. So that basically means that I'm going to be running the meshes where the medium mesh will have half the number of cell sizes as the fine mesh, and similarly the coarse mesh will have half the number of cells as the medium mesh. What I'm going to do is I'm going to examine the drag coefficient and the lift coefficient as the mesh is refined, and this is essentially the single variable grid convergence index method. But I'm also going to take a look at how the pressure coefficient around the airfoil behaves as the mesh is refined, and this will be interesting because not all of the points on the airfoil will actually monotonically converge, and we won't be able to use the grid convergence index method for all points on the airfoil. And finally then I'm going to compare it with the experimental data with an 8.4 degree angle of attack. So essentially I'm going to run this NACA2412 airfoil at 8.4 degrees so I can compare my estimated results with the experimental data. So let's get jumping into Ansys. So what I've done here is I've just opened up the NACA2412 file that I finished off with in my previous video in the NACA2412 tutorial. And if you've watched that video, then you can just simply follow along with this tutorial. Or if you're using a different study, such as a different NACA airfoil or any other study, you can just use this approach however it suits your particular simulation. So the first step I'm going to do is I'm actually going to go back into the mesh. I'm going to take a look at the number of mesh cell sizes and take a note of that, and I'm also going to just make a few changes to the mesh because I wasn't quite happy with the quality of the mesh in the previous video. So I'm just going to refine the mesh a little bit more to make it better quality, and then I'll make a coarse mesh, medium mesh, and a fine mesh. Now going back to my slides here, the first step here is to characterize or to create a characteristic cell size. But if I go back into Ansys Mechanical here and look at my mesh, I actually have quite a structured mesh here where I have, in this area here I have the same mesh size, in here I have the same mesh size, except for the fact that I have a bias factor, and that's due to the fact that I've used edge sizings here. So what I'm going to do is I'm going to basically I'm not going to define a characteristic cell size, but I'm going to reduce or increase the number of divisions by my refinement factor. And this would also work, for example, if you have a simulation with an edge sizing of say 1 millimeter, you can reduce that size by a factor of √2 if you want to use √2, or 1.5, as long as that number is greater than 1.3, then you're good to go. So in this case, I'm essentially going to reduce the number of divisions by √2, for the fine mesh and increase the number of divisions by √2 for the coarse mesh. But I've just noted that if you are running a case where you have element size as your edge sizing, you would have to decrease the element size by your refinement factor for the fine mesh and increase your mesh size by your refinement factor for the coarse mesh. So let's take a look at the mesh here. And this is what I wanted to fix in my mesh. You see, there just is a little bit of a area here where the mesh just goes into quite a sharp transition shape size. So I'm going to go back into Design Modeler and I'm going to change that. But let's take a look at the number of cells that we have in the mesh here. So we have about 200,000 cells. So we're expecting that in the fine mesh we should have 400,000, and then in the coarse mesh we should have 100,000. So I've just exited mechanical and I'm going to go back into Design Modeler and just make a few edits to my mesh here to get that that jump across the different elements there to be approximately at least a little bit more uniform. Okay, now that we're in mechanical here, what I want to do is I want to take this point here that I created in my sketch and I want to bring that back towards the center of the airfoil. So I'm going to create this to be about 350 millimeters, generate the mesh, and what I'm hoping is that the mesh transitions a little bit nicer from this region here into the center of the airfoil. Okay, now that I've moved this center line back to be 350 from the leading edge, there is one more thing I need to change here, and that's in the fact that these edges here have now split into two. So this front edge here I want to be defined as just the one edge, but as you can see it's split here. So I'm going to merge these edges together. To do that, I'm just going to hold down Control, select this edge and that edge, go to Tools, hit Merge, and them edges are selected, hit Apply, then hit Generate. And if I select these edges here, you can see that is all the one edge now. So I'm just going to do the same thing for the bottom edge. Hold down Control, select these two edges, Tools, Merge, Apply, Generate. Okay, so now I'm happy with my geometry, and the only way to tell if this distance that I've moved this line back far enough is good enough is just simply to go back to mechanical and to check if the mesh is good quality or not. So let's go back into Ansys Mechanical. So I'm just going to click Edit, and we want to reread the mesh in here. So going back into mechanical here, it just has lost the edge sizing here for the front of the airfoil. So I'm going to click this edge here and these two edges here and this edge here. Hit Apply and let's generate the mesh. Alright, so let's have a look. And yeah, the transition here is a lot better than it was before. If you take a look at the airfoil here, you can almost not really tell that there is that line there, especially down here. And if we zoom out a bit, yeah, that line is still visible, but it's a lot better than it was before. So I'm happy with my mesh quality here, and now it's time to refine this mesh. So if I have a look at the number of elements in this mesh, I have about 200,000 cells here. So I'm going to make a fine mesh now with 400,000 by using a refinement factor of √2. I'm going to create a coarse mesh with 100,000 cells by using a refinement factor of 2 also. So to do that, I'm just going to save the project. I'm going to go back here, and I need to update the mesh too. So let's go to update the mesh, because this is going to send it to Fluent. See, I get that it's sent to Fluent. So I'm going to close this now. So this is the medium mesh, all right, sort of the baseline mesh, if you will. Now I'm just going to duplicate this, and I'm going to create a coarse mesh and a fine mesh. Okay, there's one system, and let's just call this the coarse mesh, and create one more for the fine mesh. refine mesh. And in fact, at this stage now, if you don't want to lose your results from the previous NACA2412, what you can do is just File, Save As, and you see I've already done it here before, but let's say NACA2412 and call it what you want. Mesh Independence. I'm going to call this Mesh Independence for the video example. And now it's going to save this as a separate project in my working directory. So if I go to here to the file, to my working directory, where's the file here? You can see it's now created here Mesh Independent Video and Mesh Independent Video files, and this is why it's important to have a working directory. I've said it in the last video and I'll probably continue to say it over and over again in each tutorial. You need to have your files in a proper working directory. So in this case I just have NACA2412, and we can't save our files to documents, downloads, desktop, anything like that. We need to have a file with the name of the project that we're working on. In this case I'm fine to keep it in the same old directory as my old file, but as long as it's in a specified directory where it creates this video and files in a very small folder, so we don't lose these files. So nonetheless, I have my new file now, and I'm ready to create my meshes. So let's go ahead and create the coarse mesh first. So for the coarse mesh, what we want to do is we want to have more cells, right, than we do in our current mesh. So we're actually going to decrease the number of divisions. And we're going to decrease the number of divisions by a factor of √2. So we have 150 here, 250 here, 150 here, and 100 here. So since we have number of divisions, we want to decrease the number of divisions by a factor of √2. But it's important to note that if you're running a case where you have a cell size, what you would want to do is you would want to increase the cell size by a factor of √2. And what this is going to do is then that's going to give us double the number of cells than we had in our medium mesh. Now what I've done here is I've just created an Excel sheet here, and essentially I've just created I have the medium mesh here and the number of divisions from that medium mesh, and the fine mesh, here's my refinement factor, square root of 2, and I want the coarse mesh to be the medium mesh number of divisions divided by the refinement factor, and you can see that reduces the number of divisions there. So I've just created a small few equations here to calculate the number of divisions I need for the coarse mesh and to calculate the number of divisions for the fine mesh, and these are the number of cells I'm expecting. So going up to the coarse mesh here, this is 150 divided by √2 for looks like this number of divisions here. Divide this by √2 gives us 106 as I got here, and I've just rendered this to the nearest whole number in Excel just to make it easier. So 106, of course we can't have a decimal number of divisions. The 250 number of divisions, that's going to reduce to 177, so let's just put that in here. The 150 divisions, that's going to reduce to 106. We have two of them, 150 divisions, 106. And finally then the 100 divisions, then divide that by √2 gives us 71 divisions. Let's type in 71 and generate the mesh. And then that gives us, you can see, about 100,000 cells. And let's have a look at our coarse mesh. So quite similar, not too different, but you can clearly see that the mesh is just a little bit more coarse than the previous one, and it might be more noticeable in the fine mesh how much more fine the mesh gets. So here's our coarse mesh now. I'm happy with this. I'm going to click update, and this will be our coarse mesh case. Next, I'm just going to go to the fine mesh, and we're just going to do the same thing. We're going to increase the number of divisions by a factor of √2. So going back to my Excel sheet here, the case where we have 150 divisions is going to increase to 212 divisions. So this case here becomes 212. The other 150 also becomes 212. The case with 100 divisions becomes 141. and the case with 250 divisions becomes 354. And then click update, and that's my fine mesh done. And we'll just take a look and make sure everything's okay. Let's zoom in. And you can see here's our fine mesh now. So definitely a lot finer than the coarse mesh. And you can see here, yeah, the jump is just a little bit more obvious than before. So anyway, I'm happy enough with this mesh. That's our fine mesh. Hit update to send to Fluent, and then hit close. Okay, so that's our 3 meshes done. And there are a few more steps we need to change in the setup cell in Fluent, because we're running an 8.4 degree angle of attack case this time, so I can compare it with experimental data for the pressure coefficient. Okay, Fluent is loaded up here, and it looks like there actually is a mistake in my boundary conditions, because you can see where I had that edge before, the inlet is no longer here. So I'm just going to go back to Fluent, and I'm going to actually change that. So make sure that if you had the same case as me, where remember when I had to merge the 2 edges together, if you don't get that sort of error, if you will, then that's fine. You can go ahead and conduct your study. But what happened here is, if I go to my name selection here, since I merged them 2 edges together in Design Modeler, that changed the name selection. So the inlet used to contain this edge here, but now it doesn't. So I'm just going to go into all 3 meshes, and I'm going to change my inlet to have that there. So yeah, just make sure if you're following the same method as me that you change that in your file. Okay, Fluent is loaded up here, and I have the correct boundary conditions this time. And there is a few changes to the flow field and the properties that I need to change. Okay, and here's the experimental data. I will, of course, this is reference number 4. And I previously had in the slides, I was going to compare with an 8.4 degree angle of attack, but I believe I'm going to actually compare it with a 12.4 degree angle of attack. So going to my Excel sheet here, what I've done is just taken my 12.4 degree angle of attack, and the Reynolds number that they ran the 12.4 degree angle of attack was 2.2 million. I just have standard values for density and the viscosity here. The reference length is going to be a length of 1 meter. And the velocity, then, knowing that I have standard conditions and a Reynolds number of 2.2 million, I can calculate what the velocity of the flow needs to be. For an 8.4 degree angle of attack, we're going to have an x component of the velocity with cos of alpha, and a y component of velocity of sine of alpha. And then in Ansys Fluent, we're going to change the vectors of the lift coefficient and the drag coefficient to represent the angle of attack that we're running in this case. And I talked about this in my previous NACA2412 video, but essentially the drag coefficient, we always take the drag coefficient coordinate to be parallel to the flow. So we need to change the vector that Ansys calculates that drag coefficient to. And similarly for the lift coefficient, we have minus sine alpha as the x component of the lift coefficient, and cos of alpha for the y component of the lift coefficient. So we're going to import these values into Ansys to simulate this 12.4 degree angle of attack and to calculate the correct lift and drag coefficients. So going back to the case here, my boundary conditions are okay. The only thing I need to change from the previous study is I need to change the magnitude of the velocity. So we're running a different Reynolds number as I did in the previous video. We're going to have 32.1, let's say 32.14 meters per second. And then the x component of the flow, we're going to have cos alpha, so that's going to be 0.9767. And the y component would be sine alpha, which is 0.2147. 0.2147. Okay, that's fine. So there's our velocity. The outlet is fine. All our other conditions are fine. What I need to change is how the lift coefficient is defined. So as I said, the x component of the lift coefficient is going to be minus sine alpha, so that's minus 0.2147, minus 0.2147, and the y component is going to be cos of alpha, which is 0.9767. Hit OK. That's our lift coefficient defined. Hit edit, change the drag coefficient, and we're going to have cos alpha in as the x coordinate, 0.9767. And for the y component then, it's going to be sine alpha, sine alpha, so 0.2147. Okay, and that's our lift coefficient and our drag coefficient defined. So there's nothing else I need to change here except for the fact that our reference values have changed. So if I go to reference values, these are the values that Ansys is going to compute the lift and drag coefficient for. So you can see here it has the velocity here and other parameters. What we want to do is change this compute from to inlet, and you can see it updates the parameters to be the new boundary conditions that I've set. So that's everything I need to do here. I'm ready to run the calculation, and just to check for anyone that's running with a brand new file and not the file from my previous video, just go ahead and reduce your residuals to 1e to the minus 6, and I'm going to run this for 1000 iterations and calculate the lift and the drag coefficient. So yeah, I'm just going to initialize the solution and go ahead and start. Alright, my solution has complete here, and as you can see, I let this run for about 1500 iterations. Seems to have converged sufficiently. I'm just going to compute the final lift and drag coefficient, and this is for the coarse mesh. And what I'm going to do is just simply, this was for the coarse mesh, so all that needs to be done now is to simply run this for the medium and the fine mesh and extrapolate the lift and drag coefficients out. And we'll conduct the grid convergence index method, firstly just on the lift and the drag coefficients to demonstrate the single variable grid convergence index method, and then we'll extend this to the multi-variable, which is a little bit harder as we just have more variables to extract for each of the mesh cases. So then the next step then would I've just left this on screen for if you're following along with this tutorial, because I'm just going to jump back to my old file, which I've done it before. The next step now is to simply go to the medium mesh and make sure that the name selection is okay. So in other words, make sure your boundary condition is set correctly. Change your velocity, update your drag and lift coefficients in the tree to make sure the definition is correct. Obviously don't need to do the velocity again. So go to your medium and your fine mesh, change your name selection, change your velocity, change your drag and lift coefficient, and update your reference values as well, and run your simulation and take the drag and lift coefficients and just record them. And then what I'm going to do is jump to an Excel sheet, and we're going to calculate the grid convergence index for this case study. Alright, now I've just jumped to an Excel sheet where I've just recorded my values that I got for the lift coefficient for the coarse mesh, medium mesh, and the fine mesh. And the values here for the coarse mesh are just a little bit different to what we've seen on screen there previously, because that was my second time running it in a new file. So anyway, for your mesh, just take your coarse mesh, lift coefficient and drag coefficients, and just record them in Excel here. And I've also just put the experimental data of what we would expect, and that I extrapolated from the experimental data from this file here. So now that I've got the values for the lift and drag at the coarse, medium, and fine mesh, now I can calculate epsilon32, which is the difference between the coarse and medium mesh, just using simple subtraction, and the same for epsilon21, which is the difference between the fine and the medium. Once I do that, then I can divide the epsilon21 value from the epsilon32 value, and of course, as I said from the slides, we're expecting this value here, epsilon21 divided by epsilon32, to be between 0 and 1, and if it is, then we know we have monotonic convergence. So I just have a little few if statements and and statements here to basically say that if this is between 0 and 1, then it just types monotonic convergence here. So we're good to go. We're able to use grid convergence index method. The next step then is to calculate the apparent order of accuracy P, and I've just simply used the equation shown on screen here. So 1 over ln, the grid refinement ratio, that's what I have here, times the absolute value of the log of epsilon 32 divided by epsilon 21. So for the lift coefficient, I got a apparent order of accuracy of about 5. And then I can calculate the extrapolated variable, phi21 extrapolated from this equation here. So I just type that into Excel. And this is the extrapolated lift coefficient and the extrapolated drag coefficient. Okay, now I can graph my solution that I got for the coarse, medium and fine mesh. And instead of plotting the variable like this with number of cells on the x-axis, I'm actually going to plot the characteristic cell size on the x-axis. And to get that characteristic cell size, basically what I'm going to do is I'm going to take the number of cells and just do 1 over the number of cells. The reason I'm plotting this 1 over n is because the characteristic cell size is proportional to 1 over n. And had I have plotted the number of cells on the x-axis, the extrapolated variable corresponds to when the number of cells goes to infinity. So I would have to make my graph infinitely long, but an infinite number of cells corresponds to a cell size of 0, so it's a lot easier to plot that. But nonetheless, what I've done here is I've plotted the lift coefficient against 1 over n, so that's this point here. The medium mesh against 1 over n in the medium case, so that's this point here. Similarly for the fine mesh, and then the extrapolated variable corresponds to a characteristic cell size of 0. So this extrapolated value here is the value that we would expect to get if we were to decrease the cell size to 0, or in other words, increase the cell size to infinity. So this is our plotted results here of the characteristic cell size versus the lift coefficient. And this is why it's really useful to use the grid convergence index method, because we can get this value calculated for where we'd expect the value to go. And what I've just put here is, which is quite interesting to note, is that I've just put the experimental value here. And the reason I've done that is to show again sort of the difference between verification and validation. So of course this graph here is just verification. If we were to increase the mesh over and over and over again, we would expect the value to approach, for the lift coefficient, to approach 1.41, and no amount of refining the mesh can get us closer to the experimental value. So the difference between this point here and this point here corresponds to the sort of modeling error, if you will. This is the error that we can't capture by refining the mesh to an infinite number of cells. This error here could be due to the difference between the experiment and the CFD in terms of, could be the Reynolds number, percentage error in the Reynolds number that we can't capture in the CFD. It could be due to unsteady effects. It could be due to surface roughness affecting the solution. So the difference between this point here and this point here correspond to the sort of modeling error, if you will. So I've done the same thing for the drag coefficient, where I've just plotted the values for coarse to fine. I've used the same equations from above, so I copy and paste the formulas down here, got an order of accuracy of 4.4, and I calculated the extrapolated variable again using this equation here to get this value here. And then I plotted here on a graph, I put the coarse, medium and fine values for the drag coefficient, put the value that I calculated for the extrapolated drag coefficient here, and I've plotted the drag coefficient against 1 over n, and you can see that the drag coefficient approaches this value of about 0.0229. And then of course I put here the experimental value to show you that no matter how much you refine the mesh, you can't make up for the modeling errors. So you can see no matter how much we refine the mesh, the value for the drag coefficient will approach this value here, but the experimental value will be here. So this is the error here, the sort of modeling error, if you will, for the drag coefficient. So there are a few more calculations then I can carry out to estimate my errors, and that's using the equations shown here. So here I've calculated the relative error between relative error 2, 1, which represents the relative error between the medium and fine mesh. the extrapolated relative error, and then the grid convergence index error as well. So this final value here that I've got represents the percentage error of the extrapolated variable. So I got 0.05% for the lift and 0.36% for the drag, which are quite small values, and it actually goes to show that the difference between the experimental value and the extrapolated value, there actually is a decent amount of modeling error here. You know, this 0.05% and 0.36%, if I were to put an error bar here, the experimental value would be outside that range. So that means that the difference between experiment and CFD, basically this error is due to other errors and not just the discretization error. So if the value was in between, them error bars, you could say that the difference between experiment and CFD is simply due to discretization. But since our experimental value is actually outside them error bars, and we know it's most likely due to modeling errors, there could be other errors associated with the CFD simulation, but it's definitely not due to discretization error that our experimental value is not closer, because if you have a look, we have quite a small percentage error in our discretization error, so it must be other errors that are due to this difference. Just some other things on this Excel sheet that you might have noticed. From reference number 2, for the procedure to conduct this grid convergence index method, I've just taken the numbers from that reference, and they plotted velocity or something like that. Yeah, it was a velocity here that they plotted. I just took their numbers and used the same formulas as I did in the above cells, and pasted it in here, and I made sure that my formulas were acting correctly. And I basically got an error of 2.2% with their data, and I got 6.16 for the extrapolated variable, and that's the same as what was calculated in reference 2. So I know in my Excel sheet that my formulas are actually correct, and that the equations are right. That was just a little check I made. And then another thing I have on the Excel sheet here is I have an iterative calculation to calculate P. And the reason I had to do that for the validation case is because they used a non-constant refinement ratio. So whereas in the case here, when I used a constant refinement ratio of square root of 2, in their case they reduced the cell size by a non-constant value each time. So it's worth noting that in this case here, the equations that I've shown today in my presentation is for a constant refinement ratio, and I would recommend that you follow that approach because it's just a little bit easier to calculate P, just using a simple formula. But if you use a non-constant refinement ratio, you actually have to go through some iterative calculations to calculate P, so that's worth noting. But again, I refer you to reference number 2 if you're more interested in that. But for this case study, we're going to assume a constant refinement ratio between both the coarse and medium mesh and the medium to fine mesh. So that means we're going to take the same jump or multiply the mesh size by the same amount each time. So that was the single variable grid convergence index method, and these are the resulting graphs that I got, and the resulting error that I got was here. So again, I'll leave a link in the description if you want to access this Excel sheet. And to be honest, this wasn't too difficult to do, but now I'm going to move on to the multivariable grid convergence index method, which is just a little bit more difficult. So now we're going to plot the pressure coefficient for the coarse, medium and fine mesh and estimate the errors and basically do the same calculations for this case study. So now for the multivariable approach, it's the same equations as before, except the difficulty is we just need to deal with a lot more points in this case. So the first thing I did was I took the experimental data and I took it from the curve plotted in the reference number 4, and I plotted that on the curve here. And then the next thing I did was I had to import a multitude of different points into Ansys, and I took the pressure coefficient at them points, and then I used the same equations as before to calculate the extrapolated pressure coefficient at them points. And also you can see here that not all points monotonically converge this time, and this is why it was a little bit more difficult in this case. So if I go through here, you can have a look at the epsilon 21 divided by epsilon 32 to see which ones monotonically converge or not. But most of these points here in the center of the airfoil monotonically converge, but some points around the edges definitely don't. So all these points here where we have not a number and divided by 0 is the case where we have oscillatory convergence and divergence, and the only cases where we get numbers is when there's monotonic convergence or divergence. So I've just noted here that we're going to pretty much ignore these numbers here because we're not interested in the case when there's monotonic divergence. So the real difficulty in this approach is actually importing all the points into Ansys and then extrapolating all the data to the Excel sheet, and then finally we can conduct the calculations. So I'm just going to show you how to import the points into Ansys and how to then extract the data for one case, and then I'll leave it up to the viewer to do it on their own for the two other cases, so just the medium and fine case. But it really just is a repetitive process of doing the same thing for the two other cases. So going back to Fluent here, what you can do is you can just go here to surfaces, do new point, and just import a point here. But we want to have the same number of points and the points at the same location for each file. So what I did was I went to an Airfoil plotter, so go to Airfoil tools, and I plotted the NACA2412, and I basically extrapolated these points, and then I imported them into Ansys. And this is a little bit difficult to do, but let's go through the process. So we're going to take a 1000 millimeter chord airfoil, and we're going to make it the NACA2412. And once we have the NACA2412 here, I'm going to leave everything else and hit plot. And then I'm going to take a Excel sheet of these points. Okay, once I have my file here, I have my points, and these are in millimeters, so I'm just going to convert them to meters. And what I want here is I want to have X over C, and I want to have Y. So to get X over C, I'm just basically going to have 1000 divided by 1000. So all points here in the X are just going to be divided by 1000 to give me X over C, which is pretty much just X. And then the Y coordinates, then divide these all by 1000, bring this down, and this gives me all the coordinates that I want to import into Ansys. So these are the points that I want to import. What I'm going to do is I'm going to create an Ansys journal file to save up some of the time that it's going to take me to import these points into Ansys, because it gets a little bit tedious. And this saves a little bit of time, but again is a little bit tedious. So what this journal file does is it's essentially going to be a piece of code that records the clicks that I'm making in Ansys, and I'm going to create one point with a journal file, and then I'm going to repeat that. I'm going to essentially edit the journal file so that Ansys imports the rest of the points for me. Let's go up to File, Write, and Start Journal, and I'm just going to change this to be in the NACA2412 folder. I'm going to say journal video, right? And what I'm going to do is, once I start this journal file, Ansys will be recording every single move I make with my mouse and everything I click in a line of code. So I'm going to really limit the amount of clicks that I make if that aren't associated with creating a point. So I'm going to hit OK. Now I'm going to go to File, New Point, and we're going to create the points that are on this Excel sheet here. So the first point is at X equals to 1 and Y equals to 0.0013 meters. So X is equal to 1, Y is equal to 0.0013 meters. Hit cell center and then hit create. So that's the first point now. Now for the second point, 0.95, and the Y coordinate is 0.0114. Hit create. Now I'm going to do two more points, 0.9, 0.0208, hit create, and finally 0.8, 0.0375, 0.8, 0.0375. 375. Hit create. Now let's have a look at the points. Well, first we need to stop our journal file. So file, stop journal. Okay, and I'll talk about this journal file now, but let's just take a look at the points first. Hit display and display all 3 points. So then points are imported. But we don't want to type in all the rest of the points that are around the airfoil. So let's take a look at our journal file and see what we can do to speed the process up. So if I open journal video in a notepad and take a look at the file, this will show me all the actions that I took from when I started the journal to when I ended the journal in a piece of code. So you can see here that the first part is when I sort of started the journal, and then from this point on, the journal gets pretty repetitive, as in this is the X, this is the Y of the last point I put in, and this is the X, this is the Y of the second last point I put in, and this is the X, this is the Y of the third last point I put in, and so on. So these lines of code here are pretty repetitive, and I can edit this file to essentially import all the points for me. So if I were to for example, take this point here, this is the piece of code I want to repeat. I want Ansys to import the next point for me automatically. So that's going to be 0.7, 0.518. And the next point is 0.6, 0.0636. So I'm just going to copy these lines again. Zero point 0.0636. And I'm basically going to follow that for all points, and I'm going to get rid of some of the mess here. So I do want all this here. Let me have a look. Yeah, I do want all cell centered values, and I want all these points to be imported. And it's important that you put it in above this cancel line, because this is obviously going to end the insert a point command. So what I essentially done in another journal file is I created the journal file, and I put in every single point in here that I have to import into Ansys. And then what I can do is I go into Fluent, read, journal, change this to all files, and then I'm going to go to the journal points that I had there. So really it's a little bit of tediousness to go in and create this file, but it just means that then you can import these points into your coarse, medium and fine mesh and have all them points there, rather than import the points manually on your own. Now unfortunately it's not as simple as just that, because as you're going to see when I import this, hit yes, not all points are going to come in, so just hit yes. Some of them are going to fail because they're not going to be inside the mesh, and I'll show you what I mean by that. So hit close. So now it's imported the majority of the points in from reading my journal file. But if I show all the points here by just holding shift and highlighting all the points, hit display, you'll see that some of the points have actually failed. And basically if you're lucky, most points will come in, but unfortunately sometimes some of them fail. So then again, it just takes for the coarse, medium and fine mesh, you import the journal points, and some of them are going to fail. So what you're going to have to do is basically just go in and manually put them in. So it looks like the one that failed here is, if we go 1, 2, 3, 4 from the edge and check what point that was, it was on the one on the bottom face. Was 1, 2, 3, 4 from the edge. It looks like this point failed, so I'm just going to have to import that one manually, and I'm basically just going to have to do this for every point. Looks like we have 0.7 and minus 0.0214, 0.7 minus 0.0214. Hit cell center, and sometimes you might have to change the name of the point you're importing. I'm just going to call it 100 because in case the name has already been in here. hit create, and it looks like that one created okay. Hit display, and I'm going to display that point 100. So that one actually imported okay. Let's move on to the next one. And sometimes we can get an error if the point is not inside the mesh, and I'll show you what I mean. Maybe if this next point gives me an error. So 0.6 and minus 0.0276. Hit create. I'm going to call this 102 just because I'm not sure. Sometimes it can give you a name which is already in the tree and that creates an error, and sometimes it doesn't. Hit create, and you can see now I get surface creation failed. Now the reason for that is because the point I'm trying to import is just above outside the mesh, so it's not actually in the domain. How I fix this is just by bringing it inside the domain. So if I take the Y coordinate here and click on the edit box, I can now drag this into the mesh. Actually, I might have to make a small change, maybe make it to minus 0.0275. That brings the point up a bit, and now I can drag it just inside the mesh like that, and then hit create. Okay, so what I would do for all of these points is I essentially, when I did this, was I went around, checked here. It looks like the 0.5 and 0.4 point went in okay, but the 0.3 point error was an error. So I went in here, took the 0.3 point, imported that into Fluent, and then changed the Y coordinate to be just inside the mesh, and then that gives you finally all your points around your airfoil surface, and then we can export the data. So it is quite a tedious process to import the points, but nonetheless the journal file speeds it up a little bit, but you have to kind of go in and manually edit some of the points that don't go in. So I'm just going to skip ahead here to the old file I had before, where I went through the time and the effort to put in the points and make sure that they imported okay. And I'm going to show you how to then export the pressure coefficient at each of the points. And don't worry, I will leave these files, a link to these files in the description, because I wouldn't want anyone watching this tutorial to have to go in and import all these points one by one. So I will leave a file. I will leave this file with the majority of the files in the description, and you can do a couple of things. You can simply open up the Ansys file and have a play around with it yourself and export the pressure coefficient there, and then create your Excel sheet and try and match my results. Or you can just take my journal points, maybe put that in, get a bit of practice messing around with the journal file as well. Or you can just simply use my Excel sheet, examine the results, and use that to adapt it to a different study. So whatever suits the viewer. So here's my file here for the coarse mesh. I'm going to hit display, just all the points here, and you can see that I have all of my points on the Airfoil here. So I went through, imported my journal file, edited all the points so that all points were here. So this gives me all of these points here on my Airfoil. So the next step then is going to be exporting the pressure coefficient for this file. So I'm going to go File, Export, Solution Data. I'm going to export it as an ASCII file, or I don't know how you pronounce that, ASCII, whatnot. I'm going to go click point surface, so I want all the points, and then I'm going to export the pressure coefficient at the cell center separated by a comma. Hit right, go back to my working directory here, and I'm just going to call this file, say I call this is the coarse CP file, so I'm just going to call this, I already have this file here, coarse CP points number 2, say. Hit OK. I'm going back to my working directory. Let's take a look at the file it created. So here we go. Now it's exported the pressure coefficient and the x coordinate of that pressure coefficient. So what I can do is now import this into my Excel sheet. So to do this, what I basically did was I moved to a new sheet here. I'm going to press Ctrl V, edit this here, use text import window, and we have a delimited text file here that's separated by not a space but a comma. hit next and finish, and now it imports it in as the number of columns. I don't need the y coordinate, I just need the x coordinate and the pressure coefficient, and I don't need the cell number here. So that's essentially what I've done for the coarse, the medium and the fine mesh. Is I just went, edited the text, exported the file, got it into a text file like this, and imported it into Excel, get it in the columns, and then what I created a nice table here with all my different points for the x coordinate, the pressure coefficient for the coarse, medium and fine. And I actually did rearrange all these points to in the Excel file, because it looks like we have here this starts at 1, then it goes to 0.25. That's pretty much 0, so there's no order to the points, so I actually just ordered the points here as well. So once you've exported the pressure coefficient at every x coordinate, then you can just bring it back into this sheet here, and this is essentially gives you all these points here. This is the pressure coefficient versus the x coordinate for the coarse, the medium and the fine mesh, just put in order, and I've just rearranged the data. And I also have the experimental data here on the very left hand side. So the first thing you can do then, once you have all the data exported, is you can just create some graphs. So this is the nice graph that I ended up with at the end. So if you don't have this graph yet, how you do it is just take the coarse mesh here, hit insert. I'm going to create a graph. I'm just going to call this one coarse. I'm going to take the experimental data and plot that on a curve too, because the goal here is I want to put all these coordinates on the one graph. I'm going to call this, say, experiment. Okay, here's my 4 different graphs, and now I want to put them all on the one graph, so I'm going to press Control C to copy this coarse graph, go back to the experiment, hit Control V, and it imports my coarse data onto this data here. I'm just going to hit the legend here. I know I can change this later, but I've put my coarse data on here, but I don't know which is which now, so I'll deal with that shortly. Now I can delete that graph, medium, paste that on here. Looks like the medium was the gray, and then copy, paste. So now I have all of my points on the one graph. And then from this on, it's basically just formatting the graph and changing the legend to the respective data. So how I did that was, if I go to my graph here, hit select data, hit series 2, and have a look at what column that is. That's the experimental data, right? So I know instantly series 2, this is experimental data. Hit OK, hit OK. I would redo that for the coarse, medium and fine mesh, and then when I hit the legend here, it shows me which is which. So that's experimental data compared with these data here. And I also cleaned it up a bit. I put some titles on here. Okay, so that's how I got that graph there. And then I copied and pasted the formulas in from the previous slide onto on the previous sheet, I should say, onto this sheet. And I was able to calculate the extrapolated value for the pressure coefficient at each of the points. And now what I can do is I can plot a graph of the extrapolated variable at each of the points. So I'm going to just create a sort of dummy graph here of the coarse data, and then I'm going to change the y coordinate to be the phi21, and this is the extrapolated pressure coefficient. And as you can see, it looks like the coordinates on the bottom part of the airfoil, where the coefficient of pressure is negative, you know, actually there's a lot of points here in the middle of the airfoil which don't monotonically converge with the mesh, so we can't really validate 10 points, but a lot of these points we can kind of validate. And yeah, if the viewer is interested, you could also plot this extrapolated data onto this data here. Actually, I'm going to take, since I want to keep this curve, I'm going to copy this onto here and make this a lot bigger. And unfortunately, my series have been unnamed again, but the yellow data is the extrapolated data, and you can sort of examine where the extrapolated data sort of goes to. So taking a look at these curves, you can see it's actually the values I calculated here for the coarse, medium and fine mesh are actually really similar, which is surprising. But there's some points here on the bottom part close to the trailing edge which differs a little bit. And the coefficient of pressure doesn't really change too much with the mesh. If I really zoom in here, it looks like at the coarse mesh, yeah, the coarse mesh, medium and the fine mesh are really quite similar. Yeah, there is some difference, but it's really quite small. So it's quite interesting to note that the pressure coefficient in this case study was predicted quite well, and that the extrapolated data it looks like it's represented the experiment quite well. There are some points where there are differences, and especially due to the fact that the lowest pressure coefficient simply isn't predicted well by the simulation. It's just not captured. So I would say that this point here, the minimum pressure coefficient close to the leading edge, this could be due to modeling errors or unsteady effects that aren't captured in the CFD simulation. And also here you can see I've plotted the relative errors and the grid convergence index errors, and you can see probably the greatest error here is this point here at x over c is equal to, I think it's about 0.95 near the trailing edge of the airfoil. There's about 20% error there in that point there, so there is higher magnitudes of error in the pressure coefficient case. So finally then, I've just put some references here that I would recommend reading if you're interested in this further. The first reference here is a paper that talks about the procedure for error estimation in CFD. It talks a lot about the grid refinement method or the grid convergence index method and how it's important to have a low iterative error. The second paper then is the Journal of Fluids procedure for conducting the grid convergence index method that I conducted in my Excel sheet here. The third study then is a paper by Roach that conducts the grid convergence index method, and the fourth one then is the experimental data that I used, and I will leave a link in the description for you to gain access to these files here, so you can play around with the files yourself, maybe have a look at my Excel sheet. And what I would encourage anyone that is doing publication level studies to go through at least a single grid convergence index method yourself, calculate, put these formulas into Excel, have a look at reference number 2 and try and basically follow the procedure yourself for a different case study, for example, and plot curves that look like this, because it really will cement your understanding on what this method is doing. And yeah, you will be publishing some high quality standard mesh independence studies in your work. But yeah, nonetheless, that's all I have to say for today's video. I hope you enjoyed, and yeah, leave me a comment on what you thought. I know it's definitely going to be a long video, and there was quite some tedious stuff, especially in terms of importing the airfoil points. But if you followed along, I hope that you learned something, and I hope you enjoyed. So yeah, thanks for watching.